As promised, here is your video that's going to go through and correct the study guide. So again, you can use this as a resource to help look at yours and figure out where your strengths and weaknesses lie, and if you have questions for me. So topic 1 is identifying the 3 types of chemical bonds, covalent being one of them, followed by ionic and metallic. I can state the number of valence electrons that an atom attains to be most stable. Most of them want 8 valence electrons. Again, there were a few that have exceptions, and we'll talk about those more later on. Why do elements form chemical bonds? So the whole basis of that is to complete their valence shell. Filling that s and p orbital to give it electron stability. So the 2 types of compounds, they can either be an ionic compound or a covalent. So let's see, I can define ionic, covalent, metallic bonds in terms of the type of elements, metals, and nonmetals from which they are formed. Ionic bonds contain a metal and a nonmetal. Covalent is typically nonmetals, if I can write an M, with a nonmetal. They can sometimes include metalloids as well. And then the last one, metallic bonds are definitely metal, like alloys, okay? So I can define ionic and covalent bonds based on what happens to the valence electrons. So in an ionic bond, the valence electrons of the blank, so we're filling in lots of blanks here, of the metal are transferred to the nonmetal so that each atom attains a stable octet. In a covalent bond, the valence electrons of 2 nonmetals are shared. So it goes back to number 3 on the whole reason why chemical bonds form. It's because of the wanting to get that electron shell filled with its octet, meaning the S and P are filled. So those majority are the majority of topics from 7.1. So the next big one is Lewis structures. So just some things to review. How many electrons does hydrogen require? Again, it doesn't want an octet. It's satisfied with a duet. Which elements make up an octet? So the 2 that you want to look out for is boron and beryllium. They typically, again, want an incomplete octet, and you complete the octet on the outlying elements. What 4 elements have the ability to make a double or triple bond? Remember, there's an acronym, CONS: carbon, oxygen, nitrogen, sulfur. And which nonmetals have the ability to form an expanded octet? So those are the nonmetals that are found in period 3 onward down. So here's a list to kind of give you an idea. We have phosphorus, sulfur, chlorine, argon in period 3. Period 4, we have selenium, bromine, krypton. Moving down another row, we'll say iodine and xenon. And the last one we'll go with for period 6 is radon, and we don't really need to worry about period 7. Okay, so those are some things to look out for on your test with Lewis structures. So then from here, you're drawing out the Lewis structure. Water has 8 valence electrons, so H bonded to O, bonded to an H, lone pair on the oxygen. I2 has 14 electrons. You have enough to complete your outline octet, and that's your Lewis structure for I2. This one you have to be careful with. ICl3, you have 28 electrons to spend. I is your center. Go ahead and add your chlorines. And then from here, you need to be careful with your iodine. So right now I have 24 electrons. And so from there, you have, if I remember right, I said you have 28 to spend. So we end up with 2 lone pairs on the iodine here. And if we count, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. And so that one's kind of the odd duck out of the bunch. Carbon dioxide. So carbon dioxide has a grand total of, it looks like 16 electrons. This one, you do not have enough to complete your octet. So we have 2, 4, 6, 8, 10, 12, 14, 16. So 2 double bonds are required for that molecule. Methane for CH4 has 8 electrons to spend. And there's your Lewis structure there. And then phosphorus hexachloride should be surrounded by 6 chlorines. And you will have enough electrons to then complete the octet on any outlying elements. And it's all set. So then how many electrons are formed in a single bond? So a dash, remember, represents 2 electrons. A double bond here between the C and the O, for example, is 4 electrons. None of the molecules I had you draw require a triple bond, but remember that's 6, and you potentially could see those again on your test. So then you're doing VSEPR to the molecules above. So water has 2 bond pairs, 2 lone pairs. The resulting shape is bent. Iodine has 1 bond pair, 3 lone pairs. That's going to be linear. The ICl3 has 3 bond pairs, 2 lone pairs. Carbon dioxide, and I'm going to have to get my table out here in a second for the angles and the shape. I can't remember if this is T-shaped or if it's something else. So CO2 is 2 bonds, again, not 4. Again, central molecule and single, double, triple bonds all count as 1 lone pair. Methane has 4 bond pairs, no lone pairs, and PCl6 has 6 bond pairs, and none of which are lone pairs. So let me grab my sheet real quick. Just like always, I did an excellent job hiding it from myself, so I believe I have it open. There we go. So I will go back here in a second so you can see my sheet. So 3 and 2, it looks like that's T-shaped. So then 2 and 0, that looks like that's going to be linear with the 180. So then 4 and 0 is tetrahedral. And it looks like 4 and 0, tetrahedral 109.5 for the angle. 6 and 0 is going to be octahedral with 90. And I got a few angles to go back for. So T-shaped has an angle of 120. Linear, this is where we get the weird one. I think 1 and 3 it has NA. So we'll just put NA for that one. And 2 and 2 bent is 104.5. So thanks for bearing with me on that one. So going back to the screen, you actually probably want to see is this is how your table should finish up for VSEPR. Again, if you have questions about that, let me know. So from there, this is getting into our last topic, polarity. So I can explain the difference between polar and nonpolar and the types of nonmetals involved. So a polar covalent bond is formed when blank nonmetals share electrons. And so the key thing here is they share electrons unequally. And I really think I meant to have it say 2 nonmetals is why that line was so long. So the next part, nonpolar covalent bonds are formed when this is going to say 2 nonmetals share electrons equally. For 11, the degree of polarity of a covalent bond is determined by the difference in electronegativity. So that's how you can tell a bond is going to be polar in terms of nonpolar or polar covalent, and then ionic. So then in 12, you had to find the bond that was more polar, and so you need to know the difference between them. So H and P, we have 2.1 and 2.1, so that's 0, as where we have H and C is going to have a difference of 0.4. Therefore, that's going to make it more polar compared to the other. OF and OI. OF is going to have a difference of, it looks like 0.5. OI is going to have a difference of 1. Differences of 1 is definitely going to be greater there. N and O, or S and O, so the bond between a nitrogen and an oxygen, results in 0.5. S and O results in a difference of 1. So all three on the right are more polar because it has a greater difference in their electronegativities than the ones to the left. So then here you're just filling in the table, kind of like what we did in the assignment notes. So sodium has an electronegativity of 0.9 and F has 4. So the more electronegative is 4, sodium is 0.9. So your difference there results in 3.1. So that's definitely ionic. It's greater than 1.7. Hydrogen and oxygen, so the more electronegative is the oxygen with 3.5. Hydrogen is 2.1. So our difference there is 1.4. And that's going to put us in the polar covalent range. C and H, carbon is 2.5. Hydrogen's 2.1. Difference there is 0.4. And we'll put that in the polar range. And it looks like F and H, fluorine will definitely be the greater of the two. H is 2.1. We end up with a difference of, and actually this one we're going to make nonpolar. So C and H is going to be nonpolar because of the greater than equal to thing. I forgot about that. So then 4.0 minus 2.1, we have 1.9. And that's definitely going to also be ionic as well. So we have a mix of all three types. Just review that table. And again, you can go back to the notes on polarity. So then the last topic, learning target as well for this particular lesson, is looking at the overall molecule and deciding if it's polar or not. So this one, we just drew water not too long ago. So then it wants to know what's the deal. This is going to be a polar molecule. And it's because you have lone pair on the central atom. So then you also, so a lot of these you've already drawn. So iodine, and I'm going to be lazy here just to save time. So this is also going to be polar again because there's lone pairs surrounding that central atom. So here we have carbon dioxide. This one, we had the double bonds. So a lot of times people see the double bonds and they assume polar. This one is actually going to be nonpolar. And it's because the central atom, A, has no lone pairs, and B, surrounded by the same element. So again, the way I think about this is like a game of tug of war. So carbon is being pulled on by oxygens of the same electronegative value. There's no extra lone pair electrons for the carbon to hoard, so that's where it's going to make it a nonpolar. So then the last molecule with methane, that's really H's because I'm not paying attention to what I'm drawing. So carbon surrounded by 4 hydrogens, and actually the reasoning here is going to be the same. It's nonpolar as well. There's no lone pairs in each case. Neither carbon has a lone pair on the central atom, and they're surrounded by the same elements. This one just happened to be double bonds. The one below just happened to be single bonds. So this was your quick run through on your study guide. If you have any more questions, concerns, please let me know.